Welcome back to Forge College. So, for those of you who joined us for our previous explainer, you can go ahead and take off those high-speed Solana hats. Today, we're shifting gears right into our Ethereum fundamentals track. Specifically, we're tackling the life cycle of an Ethereum transaction. So grab your heavy-duty safety goggles because we are looking directly under the hood of the EVM for a deep dive into gas mechanics.
Consider this your engineering schematic for the day. Here's the agenda. First, welcome to the engine room. Then, we'll look at the baseline, intrinsic gas, followed by the mileage, execution gas. After that, we're building the gas calculator and finally putting it to the test.
All right, Section 1, welcome to the engine room. Let's completely flip our perspective on Ethereum gas for a second. Instead of looking at it as some scary financial fee, today we're treating gas as the literal physical fuel that powers the EVM engine. I mean, it's pretty simple. No fuel, no combustion. No combustion, no execution.
This perfectly illustrates the duality of our fuel math. We're looking at two main parts here. First up, intrinsic gas. You can kind of think of this as the toll booth fee. It's the fixed, totally deterministic cost you pay literally just to turn the engine on. Then, on the other side, we have execution gas. That's the actual mileage you burn while driving, which, as you'd guess, varies wildly based on the exact operations your transaction is performing.
Moving on to Section 2, the baseline, intrinsic gas. So intrinsic gas is all about those fixed costs, and it's based entirely on your transaction's data fields. And the absolute beauty of this? It all happens before execution even starts. That means we can calculate it completely offline.
Think of this like a literal bill of materials. To calculate intrinsic gas, we're relying on a few very specific constants. We've got our intrinsic base fee, then a charge of 16 gas for every single non-zero byte of call data, which remember is just the data payload you're sending with your transaction. We also have 4 gas for every 0 byte. Oh, and if you're creating a brand new contract, there is a massive 32,000 gas surcharge for that.
But really, the crucial point here is this golden number, 21,000. Seriously, I want you to memorize this one. 21,000 is the baseline intrinsic cost that absolutely every single Ethereum transaction pays just to get verified. It doesn't matter if you're transferring millions of dollars or just writing hello world to the chain, you are paying that 21,000 gas toll just to enter the network.
So, to summarize all that, our intrinsic gas equation is actually incredibly elegant. It's just the base 21,000 plus that contract creation surcharge if you happen to need it, plus the per byte call data cost. You just do the math on those specific fields, and boom, you found the exact baseline cost of your transaction.
Section 3, the mileage, execution gas. Okay, so what actually happens once the engine is running? Well, this is where we calculate the precise amount of fuel burned for every single operation the EVM performs during runtime.
You see, every EVM instruction, or opcode, consumes totally different amounts of fuel. It's honestly like comparing a tiny moped to a heavy-duty tank. Simple math operations, like add for instance, they just sip fuel at 3 gas. But look at SS store. That's when you're writing new data directly to the blockchain storage. At 20,000 gas, it is a massive, total fuel guzzler of an operation. Reading from storage with S-load, on the other hand, is a lot lighter, coming in at 800 gas.
Now, we also have to account for memory, and this is computed dynamically. The EVM charges 3 gas per memory word, but listen up, because here is a major warning. Do not double count memory expansion when you're looking at your transaction's step-by-step trace. The EVM only charges when the memory footprint actually increases. Think of it like a house. You only pay for the new room you build, not for the rooms you already paid for.
All right, Section 4, building the gas calculator. Time to put on those mechanics gloves. We're going to take all this theory and turn it into a concrete, offline diagnostic Node.js script, a script that will process transaction files and spit out exactly how much fuel we're going to need.
So, here's the logical assembly of our code. Step 1, calculate the intrinsic gas by parsing the payload. Just a quick pro tip here, be super careful to strip that 0x prefix from your hex data, otherwise you are definitely going to miscount those bytes. Step 2, sum up the execution opcodes and calculate any memory expansion from the trace. And finally, Step 3, compare our required total to the gas limit. Which naturally brings up a pretty important question. What happens if the tank runs dry mid-journey? Well, your transaction has a gas limit, and this acts as a hard, unbreakable boundary. If the total gas required ends up exceeding the gas limit you provided, the EVM just slams on the brakes. The transaction fails, it aborts, it reverts. And the worst part? You still pay for the fuel you burned, but all your state changes are completely undone.
Section 5. Putting it to the test. Let's boot up our shiny new diagnostic machine, run our script against 3 specific sample files, and let's see if our logic actually matches the EVM's internal accounting.
For our first test, TX1, we're looking at an empty data transaction that makes an external call and writes to storage. Now, because the data is empty, the intrinsic gas is exactly our golden baseline, 21,000. The execution? That's 700 for the call, plus 20,000 for that super heavy SSTO, giving us 20,700. Add those two together, and we get a total of 41,700 gas. Nice, clean, and accurate.
Okay, let's ramp things up a bit with TX2. This one is a contract creation with 16 non-zero bytes of call data. Just notice how the intrinsic gas absolutely spikes here. We've got the 21,000 base, plus a massive 32,000 contract creation fee, plus 256 for those call data bytes. That is 53,256 gas burned before execution even begins. The execution itself is actually just some light math at 113 gas, bringing our grand total to 53,369.
And finally, TX3 tests our memory expansion logic along with multiple S loads. Here, our intrinsic is slightly elevated at 21,040, mostly due to some 0-byte cow data. But check out the execution, 2,400 for 3 S loads, plus about 30 gas for expanding memory out to 10 words. We validated that we only charged the delta for the actual footprint increase, which brings our total to a very precise 23,470 gas.
All right, let's lock this all into memory. Here are the 3 core takeaways from this explainer. 1. Intrinsic gas is fully deterministic. You can compute it completely offline based purely on transaction fields. 2. Execution gas is a runtime accumulation of your opcode and memory costs. And 3. The gas limit is your hard execution bound. If you don't provide enough, your transaction aborts and you go absolutely nowhere.
So we've successfully calculated our totals, but that leaves us with a pretty fascinating question for next time. How exactly does the EVM consume this total gas one specific opcode at a time during live runtime? Well, we're going to answer exactly that in our upcoming explainer on EVM bytecode execution. Until then, remember that this explainer was proudly made by Forge College. Be sure to visit our website at forge.college to continue your journey and dive even deeper into Web3. Keep building, and I'll see you next time.